Today we are going to talk about orbits. So we are going to start from the definition of an orbit. So what's an orbit? In this diagram we are seeing that an object is rotating around another object. So starting from this diagram we can define an orbit as the curved path of a celestial object or spacecraft around a star, planet or moon. An orbit is a regular repeating path that one object in space takes around another one. To a close approximation, planets and satellites follow elliptical orbits with the center of mass being orbited at the focal point, or the ellipse as described in Kepler's law of planetary motion. We will discuss about the Kepler's law of planetary motion in another video. Planets, comets, asteroids, and other objects in the solar system orbit the Sun. We can see in this diagram that planets like Mercury, Venus, Earth, and others, and dwarf planets, asteroid and Kuiper belt objects, and other like comets are orbiting around the Sun. So what shape is an orbit? According to Kepler's law of planetary motion, a planet rotates around the Sun by elliptical orbit, as shown below. For example, when we take Earth's orbit around the Sun and also the orbit of the Moon, aphelion is a place where the Earth is further away from the Sun, and the perihelion is a place where the Earth is near to the Sun. And also for the Moon, the perigee is a place where it's closer or near to the Earth, and the apogee is a place where the Moon is further away from the Earth. We will learn about this more in the Kepler's law of planetary motion. Now we're going to talk about orbital planes. All planets in the solar system orbit on the same orbital plane. What's an orbital plane? Orbital plane is a flat disc-shaped space that connects the center of the object being orbited with the center of the orbiting object, or easily we can say that the orbital plane of a revolving body is a geometric plane in which its orbit lies. There's an exception for here that many comets exist outside the orbital plane. Understanding orbits. There are few common ways of understanding orbits. But for now I'm going to tell you the two ways of understanding orbits. The first way is a force, such as gravity, puts an object into curved path as it attempts to fly off in a straight line. The second is as the object is pulled towards a massive body, it falls towards that body. However, it has enough tangential velocity, it will not fall into the body, but will instead continue to follow the curved trajectory caused by that body indefinitely. The object is then said to be orbiting the body. This can be easily explained by Newton's cannonball model as an illustration of an orbit by the above facts. This was a thought experiment in which a cannon on top of a tall mountain is able to fire a cannonball horizontally at any chosen speed. The effect of air friction is ignored, or perhaps the mountain is enough that the cannon is above the Earth's atmosphere, which is the same thing. If the cannon fires its bolts with a low initial speed, the trajectory of the ball curves downward to A. As the firing speed increases, the cannonball hits the ground farther. That means to B. Away from the cannon, because while the ball is still falling towards the ground is increasingly curving away from it. You can see that in this image. All these motions are actually orbits in a technical sense. They are described a portion of an elliptical path around the center of the gravity, but the orbits are interrupted by striking the Earth. If the cannonball is fired with sufficient speed, the ground curves away from the ball at least as much as the ball falls, so the ball never strikes the ground. It's now in what could be net-interrupted or circumnavigating orbit for any specific combination of heat above the center of gravity and mass of the planet. There is one specific firing speed unaffected by the mass of the ball, which is assumed to be very small relative to the Earth's mass. That produces a circular orbit as shown in C. As the firing speed is increased beyond this, net-interrupted elliptic orbits are produced. One is shown in D. If the initial firing is above the surface of the Earth as shown, there will also be net-interrupted elliptical orbits at slower firing speed. This will come closest to the Earth at the point have an orbit beyond and directly opposite to the firing point below the circular orbits. Thank you for being with me. We are going to discuss more about the Kepler's law of planetary motion and Newton's law of motion and Newton's law of gravitation in another videos. Stay with us. Don't forget to subscribe, share and like this video. Thank you very much for being with us. Thank you.